Okay. Okay, good. Our speaker is Carl Pomerance.
Hi.
Good luck.
Can you hide the
So, can I? No.
Thank you very much for the invitation to speak here. Is there like a microphone or something
Should be okay.
should be okay?
Yeah.
Okay, sometimes I'm a little soft-spoken, so I mean.
Okay, at the moment, we can only see the bottom of your face, though.
Okay, well, how if I sit down here at the screen?
There you go. Now we can see you.
How about that? Does that work? Yeah. Okay, so a few months ago, Mel asked me about an argument that I have about why there should be no odd perfect numbers. And he said I should give a talk about it in the seminar here. And I thought, well, that's not really enough for a talk. It's just, you'll see later in my talk here, it's maybe only 1 or 2 slides. But, you know, there are lots of heuristic arguments in number theory. And so I thought I'd give a talk about that. And I got to thinking about it when preparing the talk, that I'm asking the question, how closely does number theory resemble one of the sciences? So, the story doesn't begin with Gauss, but he's certainly a prominent figure in number theory, and he's also a prominent figure in science. And so let's take a look at some notes that, how do we advance slides?
The down arrow.
Not working.
There we go.
Oh, here's the clicker, okay. So here are some notes that maybe you've seen before. Up at the top, you see Primsalin prime numbers from 100, is that? Maybe 1 million to 1,100,000. They took these 100,000 numbers and broke them into groups of maybe 1,000, and he counted how many primes he found in each one, trying to determine a statistical law for them. And you can see down at the bottom of the screen, he wrote the integral of dx over lx, this is the natural log, is equal to this. So this is how many primes this function would predict for the interval. And this is how many actual primes that he found. And the two numbers are very close. And so maybe he's discovered something here. So later in life, Gauss wrote that as a teenager, he had investigated the distribution of primes. There's some notes that show that he really did. And he discovered that they tend to thin out as one gets higher. And according to the law, 1 over log x. And so you'd expect that the total number of primes up to x should then be the integral of 1 over log. Now, for various reasons, we take this integral from 0. It makes it a more complicated integral because there's a singularity at t equal 1. And you have to take the principal value there.
So, Carl, a lot of people seem to be putting something on the chat, which might mean there's a universal problem.
Okay, so where's the chat?
Someone was having problem with the slides. It's fixed now. I don't think it's an issue.
So David Seth might be having some connection issues.
Oh, all is well.
It's just very cold.
You're okay.
Is this something I can do?
No, you're fine.
Okay. Anyway,
There is a way to get rid of all the participants on the right. Which,
Oh, yeah.
Uh,
Try tapping.
Yeah, I think
So if you go back to the faces. That can help.
Oh,
I think
You minimize.
Put here, it's
yeah,
fine.
that's good.
Okay.
Thank you.
Thank you.
Okay, so this is what Gauss is predicting. And you can see that he did this for the interval from 1 million to 1.1 million. Well, nowadays we have computers and we can compute to much higher levels. And here's the exact number of primes up to 10 to the 26. And here is what the logarithmic integral of 10 to the 26 is. So that ends with a decimal point and then more numbers after the decimal point at some real number. But if we look at the quantity here, the integer part, how close it is to the exact truth. That's really incredible. It's way smaller than the square root for an error. You might wonder how Staple computed this. He didn't do it one at a time. There are too many of these. He used combinatorics essentially to compute it. For example, it's not very hard to compute how many odd numbers there are up to 10 to the 26. You don't have to count them one at a time. And you can use arguments like that to get to the exact number. Now, Gauss didn't supply a proof for his law, and even for the far weaker relation, which is known as the prime number theorem, that pi of x is asymptotically x over log x. That would wait a century after Gauss's teenage years to Hadamard and Delaunay Poisson. But we still don't have what a proof that the error is as small as it apparently is. Now, Riemann made a contribution about a half century later, and he introduced the Riemann zeta function, which was actually a function considered by Euler, but Euler had it for S as a real variable, and Riemann had S as a complex variable. And he showed in his 1859 paper that if the zeros of this function with positive real part have actual real part equal to 1/2, then the number of primes up to x is equal to the logarithmic integral at x, plus an error that's just a tad bigger perhaps than the square root. We now know we can actually prove that this is the inequality, that if this inequality holds for every x starting at 2, then the Riemann hypothesis holds, and vice versa. This is equivalent. I like to describe this as the calculus class description of the Riemann hypothesis, because calculus students can understand the logarithmic integral. This is just an integral. It's the kind of thing on a calculus test that a teacher would say, find the derivative of the function defined as, and then give the logarithmic integral function. Anyway, pi of x is easily defined. And so a calculus student can understand the statement, and it's equivalent to the Riemann hypothesis. You come up with one value of x where this fails, then you've disproved the Riemann hypothesis. Okay, here's another way of thinking of this. Suppose we go through all the natural numbers and we assign the word prime to n with probability 1 over log n. Now, I would not do this for n equal 1 or 2, but I could do this for n starting at 3. And the question is, what can we say about the number of integers up to x which are given a prime label? Now, expected number is clearly this logarithmic integral. It's the sum of 1 over log n, which is essentially the integral of 1 over log t. But in fact, the error is expected to be really, really small, again, about the square root. And so this can be viewed as, that's what's happening with the primes, that we have, you know, some super being, the supreme fascist, as Erdős would say, assigning labels to numbers with probability 1 over their log. And that's what's happening with the prime. And you can also go after the Riemann hypothesis itself as a scientific statement that needs verification in the real world. And you can actually try to compute the zeros and see if they lie on the line 1/2, real part equal to 1/2. So Riemann himself found the first 3 zeros and found that they have real part equal to 1/2. Alan Turing had an algorithm for this. The current champions are Platt and Trudgian, and they showed that the first 1.2363 times 10 to the 13 zeros are on the 1/2 line. Okay, we've now dealt with the Riemann hypothesis. Okay, let's move on and deal with the twin prime conjecture. So the weak form of this conjecture merely asserts that there are infinitely many pairs of primes that differ by 2. The still weaker form says that there's some fixed integer g, which is a gap between 2 primes infinitely often. And this still weaker version was proved not so long ago, maybe 15 years ago, by Yitang Zhang, with improvements by many others. And we now know that there's some positive integer g smaller than or equal to 246, which is a prime gap infinitely often. However, we do not know any specific g with this property. What is the strong form of the twin prime conjecture? That actually counts the number of primes up to xp, with p plus 2 also prime. That count as pi sub 2 of x. Now you might be tempted to say that here's this supreme being putting prime labels on numbers with and doing it independently. Well, then n and n plus 2, they both have probability 1 over log approximately, and so we should guess that this is the count, x over log squared x, or this version of the logarithmic integral. But wait a minute, this argument that I just gave, wouldn't that work just as well as any for n and n plus 1? The supreme being says n is prime with probability 1 over log n, and n plus 1 is prime with probability 1 over log of n plus 1, which is almost the same as 1 over log n. And that's nonsense. So as good scientists, we need to go back and change our theory. We're not exactly, at least for the case of n and n plus 2, they're not independent events. If n is a prime number bigger than 2, then n is odd. And that makes n plus 2 also odd. And odd numbers have a higher chance of being prime than a random number. Also, we can look at divisibility by 3. Let's see. If n is not 3, then the number n as being a prime has to be either 1 or 2 mod 3. And those two events, 1 or 2 mod 3, should occur about equally often. Okay, good. If n is 1 mod 3, which happens half the time, then n plus 2 is 0 mod 3, and it's not prime. So we have a problem with 3. It's a 50-50 chance now that n plus 2 would be not divisible by 3 instead of a 2/3 chance. So that's going the opposite way from what we saw with 2. And we can argue that there's a constant that takes into account everything that I've just said. Here we're taking into account even, odd, And here we're taking into account primes p equal 3, 5, and 7, and so on. This infinite product converges, and we have this number, 1.32, etc. And we should put that constant in front of our modified logarithmic integral function. And that should be our conjecture. So let's check this out. Here the combinatorics isn't as good, and so we actually have to count actual numbers. And so the count isn't as robust as for primes, but it's still fairly good. And we can see that the predicted number is again very close to the actual number. And this difference is smaller than the square root of the actual number. This was computed by Oliveira e Silva about 10 years ago. So, the strong form of the twin prime conjecture, it's not proved, but as a scientist, okay, all the evidence is in, you know, we have a heuristic argument, the numbers check out, what else do you want? Okay, good. So, do we ever have to revise our understanding? Well, we just sort of did with the fudge factor C. But we'll see that we have to revise it even more than that. This fudge factor C was predicted by Hardy and Littlewood in a famous paper they wrote close to 100 years ago. But the century before, Sylvester also showed the need for a fudge factor, at least in the context of Goldbach's conjecture. Now this is getting more serious. Let's look at primes in this very short interval. We have this exponent theta being a fixed number bigger than 2. And we look at the interval x up to x plus log x to the theta. Now, this being that's labeling primes with probability 1 over the natural log would argue that the number of primes in this interval is log of x to the theta minus 1. And in fact, it should be true with a very small error term. However, it's false. It came as a great surprise when my former colleague from Georgia, Helmut Meyer, disproved this conjecture for every single fixed theta greater than 2. He showed that there's a constant, positive constant delta that depends on theta, such that infinitely often that interval has more primes than expected, 1 plus delta times log x to the theta minus 1. And also infinitely often it has fewer primes than expected. Now, how did he show this? He showed that small primes occasionally can interact in a way to have slightly more multiples in these short intervals than expected. And sometimes they gang up to have fewer hits in these intervals. The small primes also played a role, as we've seen with the twin prime conjecture, but there it's not a case of ganging up. They have a very steady effect.
What is the year on this result?
So-
Minus Meyer's result.
When the question was Meyer's result proven? It's like 1982 or 3.
Okay.
Wasn't it?
That's correct. I think he was a postdoc at Michigan.
Yeah, exactly. Yeah.
I want to point out that we don't know for sure that there are even any primes at all in such a short interval. I was once, this is sort of a funny story, I was taken advantage of from my friend Hendrik Lundstrom. He was coming to visit me in Georgia, and I was going to meet him at the Atlanta airport. This was back in the day when you could actually go to the gate and meet somebody. And I was a little bit late getting there, and I was huffing and puffing to get to the gate. And there he was coming out, and I was, okay, we connected. And he said, he was just coming from visiting in Maryland with Larry Washington and Don Zagier. And they had a question for me. It's not known if between consecutive squares, there's always a prime. Can you at least prove this happens infinitely often? So I started reciting all these deep theorems in analytic number theory. Similar, that would say, anyway. And meanwhile, Henrik was getting red in the face. And finally, I caught on to the joke that, yeah, there are infinitely many primes, and every prime is between two consecutive squares, so it happens infinitely often. So he said he lost a bet. He had made a bet with Zagier and Washington that I would immediately catch on to this joke, and they said I wouldn't, and Hendrik lost the bet. Okay, so this interval x plus log x to the theta infinitely often actually has primes, of course, because every prime is in such an interval. But the question is, can you prove that for every x there will be a prime, for every x large there will be a prime in this interval? Now, why am I talking about theta bigger than 2? That's because Pomerance had a conjecture that something special happens when theta equals 2. He conjectured that if you take the largest gap between consecutive primes up to x, then the lim sup of g of x over log squared of x is 1. So if you go to 1 plus epsilon times log x squared, you'll find primes. And if you go to 1 minus epsilon times log x squared, infinitely often you won't find any prime. Now Granville used Meyer's argument to revise Pomerance's heuristic to show that in fact the lim sup of that max gap is a constant bigger than 1. And he thinks the constant is 2e to the minus gamma, which is about, I don't know, between 1.1 and 1.2. Now the actual numerical evidence is pretty weak because the champion gaps are few and far between.
I think for this particular thing, there are 12 known champions in all the numbers that have been computed.
12, okay. So
It's on the Encyclopedia of Integer Sequences.
It's hard to do statistics with 12. Okay. We've now dealt with small intervals. Let's move on to Fermat's last theorem. So we are all familiar with the fact that Andrew Wiles has proved the famous Fermat conjecture. My question to you is, why was it a conjecture? Before Wiles, is it because we all had this understanding that elliptic curves are modular, and therefore the Fermat conjecture should be true? I don't think that that's why we thought it was true. Well, in fact, there was a paper actually of Erdős and Ullmann that gave a heuristic argument of Fermat's last theorem long before Wiles came up with his proof. And here's the way their heuristic argument worked. You let S be the set of powers, a to the n, where the exponent n is at least 4. So the number of members of S up to x is about x to the 1/4. It's dominated by the 4th powers, of course. Now let S sub 2 be the set comprised of sums of 2 members of S. So the sum of 2 powers, both with exponent 4 or larger. Now the number of members of S2 in the dyadic interval x over 2 to x is O of x to the 1/2. Now a random number between x over 2 and x, what's the chance that that random number should be in S? Well, that should be, you're only x to the 1/4 over, so it should be 1 over x to the 3/4. So we have x to the 1/2 possibilities, each with probability 1 over x to the 3/4. That means we expect the number of members of S2 in this dyadic interval that are actually in S to be small, to be smaller than 1 over x to the 1/4. And now that x runs through powers of 2, the dyadic intervals cover everything. And we expect the number of solutions to be big O of 1. And so QED, we have Fermat's last theorem. There should be at most finitely many counterexamples, at least for exponents greater than or equal to 4. Now, there are a couple of things wrong with this heuristic. Just as we had with the twin prime conjecture, the first guess was wrong. This guess is wrong too. I'll give you infinitely many counterexamples. If I add 2 to the n and 2 to the n, I get 2 to the n plus 1. And n can be any number it wants to be. And so that shows that you can have the sum of 2 powers equaling a power. Okay, so we patch this by requiring that when we add the two powers together, that they be relatively prime. And that's the situation in Fermat's last theorem. We can assume that the powers are relatively prime, so that's okay. And that kills this beast of a counterexample. There's a second thing wrong with this heuristic. Why did I say exponents greater than or equal to 4? Why didn't I go for the whole thing? Say greater than or equal to 3. Well, it's not true for cubes. I mean, Fermat's last theorem is true for cubes, but the heuristic fails. The heuristic suggests that there should be infinitely many cubes that are the sum of 2 cubes. So the heuristic was just wrong there. But anyway, we have rigorous arguments that do work for cubes. And so you could say, I'm not worried about cubes, that's something else. I just want exponents higher than 3. A similar argument that we just made for powers can also be made to show why the ABC conjecture holds. Now, is that still a conjecture? That's unclear. Mochizuki, I believe, still claims to have a proof, but many people who've looked at his argument are not persuaded. Okay, next subject, factoring algorithms. We're trying to factor big numbers. Okay, the subject has a long history. In fact, Gauss, there's a famous quotation of Gauss in his Disquisitiones, which was first published in maybe the 1790s, that the dignity of science itself we should have a fast way to factor numbers and also to prove primality. So here are some methods that we have for factoring numbers. We have trial division. That's just say, is 2 a divisor? No. Is 3 a divisor? No. Is 5 a divisor? No. Until finally you hit 1. That's trial division. We have the row method of Pollard. That involves a pseudo-random function on the residues mod n that heuristically should factor n and about n to the 1/4 time. We have the p-1 method of Pollard, which is so called because p is a hidden prime factor of the number you're trying to factor. And p-1 has the property that it's smooth and has only small prime factors. Then the p-1 method, which is based on Fermat's little theorem, will find that small prime. We'll find that special prime. We have the elliptic curve method and the quadratic sieve and the number field sieve. The only method on this list that's rigorous is trial division. All of the rest are heuristic methods.
But when you get the answer, you can check it vigorously. Once you have a factor, it's not a heuristic that it's a factor.
Yeah, as the computer scientists would say, factoring is an NP, because you can quickly check that the answer is right or wrong. In fact, I wrote about this in an article that appeared in the American Math Monthly, the notices of the AMS about 30 years ago. The article is called A Tale of Two Sieves. And I wrote, factoring big numbers is a strange kind of mathematics that closely resembles the experimental sciences, where nature has the last and definitive word. If some method to factor n runs for a while and ends with the statement d is a factor of n, then this assertion may be easily checked, as just been claimed. That is, the integers have the last and definitive word. One can thus get by quite nicely without proving a theorem that a method works in general. But as with the experimental sciences, both rigorous and heuristic analyses can be valuable in understanding the subject and moving forward.
What do you believe is true about factoring? I mean, do you think that factoring is in P?
NP.
No,
No,
it is in
Do I think that factoring is in P? Beats me.
Do you have a heuristic argument either way regarding how?
Only that we've looked at it for a long time and we haven't, I mean, this list that I showed you, they were all in existence when I wrote that paragraph in the notices of the AMS 30 years ago. And so there's no new method in the last 30 years. So we've hit a wall. And is the wall there really? Or is it just our stupidity? So, okay, it must be really there. Couldn't be that we're stupid. Okay, Mel asked me to talk about perfect numbers. And so it's his fault. Okay, a number is perfect if it's equal to S of n. S of n is the sum of divisors of n that are less than n. So if that sum is equal to n itself, then n is called perfect. The subject was actually introduced by Pythagoras. And a couple hundred years later, Euclid and Pythagoras, I think, knew the first few examples. Euclid had a formula. He said that if p, 2 to the p minus 1 is a prime number, and you multiply that prime number by the previous power of 2, and you get a perfect number. And for example, p equal 2, 3, 5, and 7 all work. If I put in p equal 2, I get 2 squared minus 1. That's 3. 3 is prime. 3 times 2 is 6. 6 is perfect. With 5, for example, 2 to the 5 minus 1 is 31. That's a prime. 31 times 16 is 496. That's a perfect number. Euler proved that every even perfect number is given by Euclid's formula. So this then leads to unsolved problems. Are there infinitely many even perfect numbers? Are there any odd perfect numbers? So let's look at these questions. So looking first at the issue of even perfect numbers. The question comes down to, are there infinitely many Mersenne primes? The Mersenne prime is a prime of the form 2 to the p minus 1. Maybe they should be called Pythagorean primes or Euclidean primes, but we call them Mersenne primes after a French monk who had a conjecture about which about which p up to maybe 127 give prime numbers. A conjecture that was almost totally wrong.
In the next line, it should be 2 to the p, right? Not 2 times p.
Yeah, I'll get to that now. So Mersenne was right in the fact that he predicted that they thin out. The first few primes are Mersenne primes, but then they thin out a lot. He was right about that. Right, and the next line I wrote 2 p minus 1, that's supposed to be 2 to the p minus 1, thank you. Now, if that's a prime, then the exponent p must be prime itself. That's why I use the notation 2 to the p minus 1. But it's not sufficient for the exponent to be prime. For example, 2 to the 11 minus 1 is 2047. That's not a prime number. And I presume that Euclid knew this, and that's why he didn't give the case of p equal 11 as an example. We also know that all the prime factors of 2 to the p minus 1, they all have to be 1 mod p. And so therefore they're bigger than 2p. Now, let's look at this number 2 to the p minus 1. Let's call it n. And we'll notice that n has no prime factors smaller than its logarithm. Now, our heuristic should say that n has probability 1 over log n of being prime. But we have to fudge that by the fact that it has no small prime factors. And this is the probability that a number should be prime then, given that it has no prime factors up to log n. Now we can use Merton's theorem to asymptotically evaluate this product, and it's a constant times log n. The constant is e to the gamma being Euler's constant. Now let's put in what n is. N is 2 to the p minus 1. So the denominator is the log of that, which is p times log 2. And the numerator is about the log of that, which is about log p. So I claim that 2 to the p minus 1 should be prime with this probability. And this, if I write this as an infinite sum over primes p, it diverges. In fact, summing it up to x, I get this constant times log x. So I would expect that the number of Mersenne prime exponents up to x is a constant times log x. There should be infinitely many. The constant should be this constant, e to the gamma over log 2. So what about experimental data? So we've computed Mersenne exponents up to 10 to the 8. We'd expect about 47 of them to give Mersenne primes, and the actual truth is 51. So not too bad. We could argue it's within square root again, but it's maybe not so convincing. But that's what we have. Now, what about odd perfect numbers? Now, Euler proved a theorem about odd perfect numbers. In fact, he proved it about every number n that's odd, for which S of n is also odd, which would be true for an odd perfect number. He showed that n had to be of the form of prime power times the square, where that prime does not divide the square, and both the prime and its exponent are 1 mod 4. This is an elementary argument just using that the sum of the proper divisors of this number is odd, and every number whose sum of proper divisors is odd must have such a factorization. Let's look at sigma of n, which is S of n plus n. This is a friendlier function than S of n, and it is multiplicative. So we can take, since the exponent j is 1 mod 4, we can take the, write it as 1 plus a multiple of 4. We can take part of those, the fourth power part into the square. And so changing notation, the odd perfect number n would be pm squared. And p would have to divide sigma of m squared. Okay. Now let's give a number m, and we ask, how many choices of p are there? Well, wait a minute. We just saw that if we're given a number m, p has to divide sigma of m squared. So the number of choices for p is limited. It's at most the logarithm of m, maybe even a little smaller than that. Now you might say that sigma of n is divisible by m squared, which it would have to be if the number were perfect, is about 1 over m squared. And there are about log of m values of n in play. So the probability is log of m over m squared. Summing this expression over odd numbers m, it converges, and so therefore we only expect to see finitely many odd perfect numbers with no, and since we've searched up to fairly high bounds, we shouldn't expect to see any. So this argument says that there should be no odd perfect numbers. Now somebody once said that they didn't like this argument because it could also be applied to even perfect numbers. And we just had a heuristic argument that there were infinitely many even perfect numbers. However, in even perfect numbers, yes, we can write them of the form pm squared, but now p is equal to sigma of m squared. It's not just a divisor, it's equal. And that never happens for odd perfect numbers because sigma is multiplicative and m is divisible by lots of different primes. And so this number can't be prime. And so we just revise the heuristic a little bit and say that p is not equal to sigma of m squared. And that rules out applying it to even perfect numbers. Okay, here's another problem. It goes back to 1932. Lamer wrote a paper about whether there exist any composite numbers n where phi of n divides n minus 1. Here phi is Euler's function. Now, it's clear that if n is a prime number, the phi of n is equal to n minus 1. If n is 1, phi of 1 is 1, and 1 is a divisor of 0, 1 minus 1. So n equal 1, n equal a prime, they're solutions. Are there any other solutions? Are there any composite solutions? He proved that such an n should be odd, square free, and have at least 7 different prime factors. I looked at this paper in preparing this talk, and he didn't make a conjecture that there are no composite solutions. It's just a question that he asks. However, he does say that it's similar in flavor to the existence of odd perfect numbers. Nevertheless, many new papers on this problem refer to this as Lamer's conjecture. Now, I actually think that Lamer was correct in his careful wording in calling it a question and not a conjecture. I think that there may be infinitely many solutions. And here's why I think that. Let's look at the residue class of n modulo phi of n. There are phi of n possibilities. What is the chance that it's 1 mod phi of n? Okay, so it should be 1 over phi of n. And the summing 1 over phi of n that's smaller than the harmonic series, 1 over n. It diverges. And so we would expect infinitely many. But wait a second though. There are certain special properties here that I didn't take into account. For example, I already mentioned what Lamer showed, that n has to be odd and square free. That reduces the number of n's in our sum, but it still diverges. However, why odd and square free? Actually, there's this stronger condition that the greatest common divisor of n and phi of n has to be 1. That's obvious why that has to be true. If n is to be 1 mod phi of n, it has to be relatively prime to phi of n. And you can ask, how often is a number n relatively prime to phi of n? And in fact, it's not that often. In fact, it's a density 0 subset of the integers. Erdős proved that the number of such n's up to x is x divided by e to the gamma log x. So that's density 0. Okay, so I have to revise my heuristic and put in e to the gamma and a triple log in the sum. It still diverges. So maybe there should be about log x over triple log x of them up to x. So why haven't we found any if there should be so many? Well, there are various other arguments going around. So, for example, this condition that n and phi of n is co-prime, I've already mentioned that it gives that n is odd and square free. If n is divisible by 3, it means that phi of n is not divisible by 3. And phi of n not being divisible by 3. Well, that says that n is not divisible by any prime that's 1 mod 3. And the statistics for those are much rarer than this Erdős bound. So that might still diverge, but we're into another problem. The phi of n is to be a proper divisor of n minus 1. It has to be less than or equal to n minus 1 over 2. And for phi of n to be small, it has to have small prime factors. And we just ruled out 2 from being a prime factor. And maybe 3 should be ruled out. In fact, 3 we can almost certainly rule out, because an elementary argument shows that if 3 divides n, and phi of n divides n minus 1, and phi of n, then the ratio n minus 1 over phi of n has to be at least 4. It can't be 2 or 3. See, you have to have a gigantic number of small prime factors, and they're restricted in the fact that each one is not 1 mod any smaller. So all of these things put together means that we have to be dealing with numbers that maybe don't have small prime factors. And then it's hard to get n minus 1 over phi of n to be 2 even. But it's not impossible. And so that's why I think that there should be examples, but they should be pretty big, and we're not likely to find them. So it has been proved that any example has to have at least 15 prime factors and be bigger than 10 to the 30. Now, this problem can be weakened a little bit, and you can ask for phi of n dividing n minus 1 to a power. And this was recently looked at by McNew and Wright. They called them K-Lamer numbers. And some actual 2 Lamer numbers are known. They proved that there were infinitely many K-Lamer numbers for k greater than or equal to 3. Carmichael numbers are K-Lamer numbers for every k, well, for all sufficiently large k. Okay, I could talk about the Birch and Swinnock and Dyer conjecture, making the rounds of number theory, right? But I won't. I'll have pity on you and myself. And I'd like to close out with a famous, semi-famous problem of Erdős and Strauss. And their conjecture is that for every integer n greater than 1, there are positive integers x, y, and z such that 4 over n is the sum of these 3 unit fractions, 1 over x plus 1 over y plus 1 over z. This has been verified for every n up to 10 to the 18, as recently announced this year by Minea and Dumitru. Now, this seems like a strange conjecture to make. Why would Erdős and Strauss make this conjecture? Well, this comes out of a sort of this cottage industry of Egyptian fractions. The Rhind Papyrus, which is a document from ancient Egypt going back over 3,500 years, has some math in it. And it shows that the Egyptians were very fond of fractions with numerator 1. They were also fond of the fraction 2/3. Let's leave that out as experimental error. They like 1 over k. And they would take any other fraction and write it as the sum of these unit fractions. Why did they do that? I don't know. They did that. In fact, Ron Graham was a big loved the subject of these Egyptian fractions, and he had this conversation once with Andre Vey, who didn't like this kind of number theory at all. In fact, he didn't even like the prime number theory. Go figure. Anyway, so Graham asked why. So why did the Egyptians study this? And they said, I guess they made a wrong turn. And that was his explanation. Anyway, okay, that doesn't explain why we have a numerator 4 here. We do have a numerator 4. Maybe the fact that there are 3 fractions is self-explanatory, because it's fairly easy to prove that 1 and 2 would have infinitely many counterexamples, and 4 or more would be trivial. So the fact that there were 3, but why not ask the same question for 3 over n, and have 3 over n be the sum of 2? Well, again, there'd be infinitely many counterexamples, as can be shown. So maybe this is the first non-trivial case, and it seems to be true. Now, they didn't have much numerical evidence. They had some, but why did they make the conjecture? Well, it's fairly easy to prove some elementary theorems about the ends for which this is true. For example, if n is 3 mod 4, then we can write 4 over n as the sum of 2 fractions, 2 unit fractions. And we could make that into 3 easily just by this trick here, if one wants, and other tricks. So, in fact, n just has to be divisible by some prime that's 3 mod 4. See, did I write that down? Yeah. Suppose n can't be written by a sum of 2 squares. Then it must be divisible by a prime that's 3 mod 4, and n is k times that prime. We've just seen that 4 over p is the sum of 3 unit fractions. And so dividing the equation for 4 over p through by k, we get that 4 over n is the sum of 3 unit fractions. So that means that the ends for which the Erdős-Strauss conjecture is false, they're all the sum of 2 squares, and that's a density 0 set. There's another quick proof that shows that if n plus 1 is not the sum of two squares, then 4 over n is representable. And so these two facts together shows that the number of counterexamples up to x is big O x over log x. That's this corollary. This idea of proving it for a prime and then getting it for the multiples of that prime, that indicates that one should be looking at the Erdős-Strauss conjecture for primes. And using this, one can show that the number of primes up to x is going to be big O of x over log of x to the 3 halves. That's because p plus 1 being a sum of two squares is unusual. So there are many of these elementary arguments, and they lend support. Mordell has a book on Diophantine equations, a famous book, and in that book he discusses the Erdős-Strauss conjecture. And he has this result that every 4 over p is the sum of 3 unit fractions for all primes p, except perhaps for p in one of these 6 residue classes, about 840. These are the quadratic residues for 840, I believe. Well, they're all quadratic residues, obviously, but I think that's all there are. Okay. Here's an elementary argument, a formula for the number of residue classes mod Q, where Q is a prime, that if n is in one of those residue classes, then, or p is in one of these residue classes, then the Erdős-Strauss conjecture is true for p. Bob Vaughan has a paper on this subject dating from 1970. And in that paper, he uses this formula and plus the large sieve to show that there are very few counterexamples. Big O x over log x doesn't hold a candle to what Vaughan proved. He has maybe x divided by e to the square root log x, something like that.
Who is the name?
Vaughan.
Ah,
E. Vaughan. 1970. It was published in Mathematica. Okay, now, if these residue classes, for which if you found yourself in one of these residue classes, then the Erdős-Strauss conjecture is true for you. They're so numerous that if they were random, we would not expect any number to escape. And that's why we think the Erdős-Strauss conjecture holds. So I recently wrote a paper with Andreas Weingartner. It's posted to the archive. That's about a week ago. And there we talk about a generalization of the Erdős-Strauss conjecture made by Schinzel. In fact, Vaughan's paper dealt with the same generalization. So here you replace 4 over n with m over n. And we still expect there just to be 3 unit fractions. M over n should be the sum of 3 unit fractions. And we show that that once you get up to e to the cube root of m, most primes, once you get up to e to the square root of m, most primes p will work. But at this smaller level, e to the cube root of m, most primes p don't work. So these are exceptions to the Erdős-Strauss-Schinzel conjecture. They don't disprove the conjecture. They didn't say it should hold for every n. They just said it should hold for sufficiently large n, depending upon m. So my question of my talk is number theory a science? I believe that it's often helpful to think that way. Proof is hard. We can still count on the computer. We can run experiments, do thought experiments, come up with heuristic arguments. We can leave the AI now to prove the theorems. Maybe. Leave some fun for us. Thank you.
Thank you.
Are there questions from
Thank
Carl
you.
in the
Oh,
room
it's
or
okay.
on Zoom?
Oh,
I was going to say, I think it's an embarrassment that we cannot prove that there are fewer odd perfect numbers. Sorry, fewer odd perfect numbers than even perfect numbers, or more. I mean, we have so little control of the number of odd perfect numbers.
Right.
I mean, all we know might be 0, which would be 5. So that's not the balance that we have.
There were many embarrassments. I can tell you one that came up recently was slightly related to this paper I have with Weingarten. Take a large number and look at the primes between m squared and 2m squared. There are lots of them. Reduce all of these primes mod n. Okay. Prove at least one of these reductions is in the interval 1 up to m over 2.
Okay.
Prove it.
Between n squared and 2m squared?
Yeah.
You've tried.
A little bit. I mean, you can prove if I replace.
Primes.
Well, so each prime should have a 50-50 chance of having reduced it mod m. Should be in the first half of the interval or the second half. And I have lots of primes between m squared and 2m squared. How can the coin come up hills every single time? Now, if I replace 1/2 m with like maybe 9/10 m, maybe I can prove it by showing upper bounds of the Brun-Titchmarsh inequality, upper bounds of primes in the big range. Maybe also if I did m cubed to 2m cubed, I could prove it.
Yeah, I think.
Okay, but I said m squared.
Yeah.
Other questions for Carl? What a quiet room.
Maybe answers,
Answers, heuristics.
as Ron Graham always used to say at the end of his talk.
All right, let's thank Carl again for a lovely talk.
thank you.
And we will be back on Zoom next week. So hope to see. Thank you, Carl.
You're welcome.
Before I shut off the computer, would one of you computer savvy people find the recording on the computer so I can copy it onto thumb drive?
To say where this e to the square root of f transition comes from in the
Square root essentially comes from the one using the word system. We have to make some changes in that uniform. Explicit. Yeah, constant involved. Unknown. Anyway, the slides for my talk are on my homepage, and so is a paper with line art plans there too.
Okay, everyone. Anyone who wants to stay for a few minutes and chat, that's good.
Mel,
Yeah,
are the previous talks available on YouTube or somewhere?
so you realize how inefficient and incompetent is the organizer of this seminar. So, in fact, because the talks, so I do have the recordings of the talks, of the previous talks, which I intend to upload to YouTube. I just have to figure out how to do it or find some 10-year-old who'll come over and show me how to do it. But I do have all those recordings. And I hope we'll also have a recording of Carl's talk that we can upload. Let me just stop recording.